是一个
最近的穿找些。
刀把路飞和我找不到，我找去的。
什么啊？你找区域补习？哦，成了啊。OK，
这也太伤心了吧！2个小时200块。
评分啊，不要便宜，没有办法哦。
对，
他不是你的问题，他听不懂。
我要澄清，
不是你讲不懂，是他听不懂。
没有没有，我比较在意的是那笔钱嘛。
其实所以我刚刚就跟他说你肯定会说这个钱要怎么。
对。什么
他说如果你能愿意从头开始教他的话，可以给你。
？I mean like 什么叫从头教？
就真的是从头讲。
我可以再重复一次。
好，
是吧？啊？
今天会拿。
还是 class 吧。哦，可是我有参考了一个I mean like 会写进来。呀，会写进来。
上周发的那个东西终于被我杀下了。
什么？
那个 .ps 的文件终于被我。
OK。
我去 online 弄了一个转换器，转换去。
要转换为我直接电脑都可以看。
不行啊！
我也是。
是 Windows 还是苹果？
要苹果，但是 Windows 应该也可以吧
？Windows 好像不行。其实苹果电脑可以。
Yeah， 苹果我是用苹果可以。你们这个礼拜有实体的 meeting 啊？
那周三晚上。
什么周三晚上？周三晚上平时都有人加面，别的组在面。
我这个要跟你们。
对啊，下周就要 present 了。下周要 present。下周14哦。
哎。
对啊，我要结束了。
我知道。
我的乖乖。
我们是这周要跟你们。对，不是下周吗？
下周14啊。
问题啊。
下周末是 present 什么？
对呀，你要 present 前才面啊，你要 present 前一周面。
可以下周面。
可以啊，只要你们
感觉这周约不上的时间。
可以啊，如果你们愿意就可以了。因为你们本身也是周一比较早的，也还就是周3比较迟。
下周一有课后嘛
Okay, let's start. So now it's week. How many week already? 13, huh? Okay. So we should have a meeting, right? For week 13, and then we have Wednesday move to next week. How about the other group, huh? Oh, Joel's group, huh? So we're meeting this week, Tuesday. What's your name?
Don't want to say
Huh? Thursday. What time?
Thursday, I want to say. Thursday.
Thursday. Okay, you guys discuss first. Thursday, I'm free now because my FYP has finished all of them, and we could meet on Thursday, yeah, before the board your what was usual before the board here. Okay, you guys discuss and then let me know. Right. So before we start, right, I have some follow up. I mean, so last time we see that this function field here of hypersurface y does it look like this? Okay, so you need to figure out the smallest fraction smallest field that contain this coordinate ring here. So I attach some lemma. Okay, so you can have a read to tell you that why this we call it minimal polynomial. Okay, let's call it minimal polynomial. This f here, why is it still irreducible? Okay, after you invert all the other variable. Okay, so I put a lemma here. Okay, actually two lemma you need. Yeah. Okay, to discuss about this fraction field here. Actually, this two lemma I pull out from Artin at the back of the chapter. I think is at somewhere around UFD. Yeah. Hey, by the way, I did abstract algebra do this kind of thing. Algebra 2. Those for those who take A2 now. Did you guys do this kind of things or not? Primitive, irreducible. Did you guys doing this? Yes or no? Yes or no? Hmm. What kind of statement you have for irreducibility? Okay. Oh, okay. Sure. Okay. I think that's the tutorial too. Right? So yeah, but I pull out these lemmas to tell you that how you figure out the fraction field. Yeah. And then I added some other things. I mean, this proof is not really important, but I mean, at least for this class. But I added in here too because I think you should be able to appreciate it. You should be able to read it. Okay. Yeah. And then when I prove the isomorphism between tangent space and the Zariski tangent space, right? We use a lot of linear dual theory here. Okay, so meaning if you know that two vector space are the isomorphic, then you know that their dual space are isomorphic. And then if V is finite dimensional, actually V and X dual space is isomorphic, then this means that their dimension is the same. Proof actually is not too hard. Okay, but you need to figure out the right isomorphism. Okay, let's prove that it is isomorphism. Okay, and then if V is finite dimensional, then V is isomorphic to its double dual. Okay, so why last time I said that it's canonical because if you want to figure out map from V to V star star here means what? V star star here means dual of a dual. Okay, so meaning this double dual here need to evaluate on V dual, which is a function. But then how do you evaluate the function? Just put your vector into the function will read out the value. That's why we call this a canonical isomorphism. Okay? Because I gave you a V, you just throw into that's it. And then you prove that this is actually isomorphism. And then corollary is you can prove that if V is isomorphic to W, then their double duo also. Sorry, they are if and only if their duo is isomorphic. Okay, one direction is easy, but the other direction you could use a double duo. Okay, and then maybe you need some other statement on linear map. So linear map induce linear map on dual space. Okay, this is very similar to our pullback. Okay, actually it's the same. Okay, but now in this case it's not variety anymore. This is a vector space. Okay, try and write it out very simple. Nice. And then where we start again. I think this one, I think mostly okay already. Next is about the tangent con chapter. Okay, for the tangent con chapter, right? There's one thing we didn't address properly last time. It's about this. Is it this? Let me see. Oh, okay. So this statement here I didn't. I'll say I didn't say it out in class. But let me tell you what is it first. So if V is a fine variety, we can define another dimension of P, okay, which we did not dim PV. Okay, this is not dim V. What is this? This is a maximum dimension of an irreducible component of V containing P. Okay, if we look at dim V, it's what maximal dimension of an irreducible component. But this one just look at irreducible component containing P. Just look at those containing P. But in dim V, you consider all irreducible components. Okay, so this is about dim PV here. So you can similarly prove that hypersurface also have dim P equals to n-1, okay, equals to dim V also. And then you could show that dimension of a cone, okay, at this point, CPV here actually equals to the dim PV, okay. So you go and do the counting, right? Still remember how to do the counting? You take the F initial. Again, you look at the 0 set. And then surprisingly, this dim PV here is equals to dim PV. Sorry, dim PCP. Sorry, dim CPV here is equal to dim. And so you are just look at the maximum dimension of irreducible component. Okay, and then there's some equivalent statement here. If P is a smooth point, then dim CP is equal to dim PV, and then if only if CPV equals to dim P. So there's one thing we didn't address properly here is if CPV has the same dimension of DPV. Okay, we know that CPV is in DPV, okay, due to the ideal containment here. Okay, so if you look at the first non-zero term, okay, non-zero degree term, it is always live in the initial part. Okay. Let me recall again. IV in here is the first non-zero initial degree part. Okay. And then I1 here is what? Is the homogeneous degree 1 part. Yeah. So your earliest initial degree that could be non-zero is the homogeneous degree 1 part. Okay. So that's why this inclusion you had it. And then, but how to show the other direction? Let's say you have a same dimension. Okay, so this dimension here is a little bit tricky, huh? Because CPV here is not quite a vector field. So this dimension is not quite vector dimension here. Okay, actually you viewed it as a variety. Okay, these two have the same dimension. Okay, in terms of variety here. Okay, and then from this lemma, you can show that actually these two are the same variety. Okay, if you have an irreducible variety here, so actually you require this TPV to be irreducible. Can I show it for you? Let me see. Can I show that this is irreducible? Did I show at any point TPV is irreducible? If not, I think I need to fill it in some way. TPV is irreducible. You can think of it as TPV is a vector space. Okay, so by change of coordinate, you can view it as the Rn. Rn is irreducible. But to write down the maps, I think needs some work. Not too hard, but needs some work. But the idea is like that. Okay, tangent space is always irreducible because you should think of Rn. Okay. Actually, our course are getting more excited already towards the end because we are doing fun stuff. Maybe you will think that it's getting harder. That's true also. Actually, can you quantify hard here? Hard is a very general concept. Anything could be hard. Can you sing or not? Singing is hard. Can you dance or not? Dancing is hard. Can you swim or not? Swimming is hard. So we want to quantify the hard here. And why singing is hard? Why dancing is hard? Why swimming is hard? Okay, these hard could mean different things. So how I quantify the hard here is these kind of things, right? You might not think about it every day. Or you never met this concept before. Okay, so this kind of hard. So once you know it, then in future you come back, you want to use it, then it will become easier. So maths, what is maths actually? It's just a language. That's all. Okay, so it's a language, it's a new language. You need to learn a new language. That's it. Okay. So but this language is a bit how to say extraordinary because when I teach this language, I teach it with concept. Usually you learn English or you learn Malay or you learn Chinese, rarely you will see concept. But they actually try to do it through one thing. Did you realize or not? If you learn language, you must learn how to write essay. You must learn how to read literature, concise literature, right? So these literature actually reflects their culture. So it's very important to read literature instead of grammar, vocab. Useless, grammar and vocab. Tata bahasa, something like that. Because if you go into the real society that speak English, speak Malay, this kind of grammar, vocab come out very naturally. I never experienced this before I go to Australia. After I went to Australia, I listened to their English or I submerged into their society. Although I don't merge that much, but it's already enough for me to understand the flow of English. It's this kind of thing is over or beyond grammar, beyond vocab. The grammar and vocab will automatically throw out and come out. No need to learn it explicitly. You understand what I say? The maths is also like that. So if you go into a stage that I don't need to tell you what is it, you have that thing in your mind already. So now what's our job here is just to make your thinking more precise so that you can talk about it. Okay 了 ，OK 了，你听得懂我讲什么 ？OK, good. Yeah, right. Okay. So please bear with it. I will try and fill in as much gap as possible. Okay, so what's our goal next? After blow up, so we're gonna do blow up now. After blow up, we'll do divisor. So there are two goals in divisor. We need to finish talking about the Zoo's theorem and Riemann-Roch theorem. Okay, these two very important theorem from this course. Okay, and then once we finish these two, we can say goodbye to each other. Okay. Right. So to talk about blow up, last time we already blow up a surface, right? Blow up a surface at a point origin, where we look at the blow up at A2 cross P1. Okay, so think about this process here. Okay, how would we generalize it? What we actually do, what's the relation between A2 and P1 here? P1 is just line through origin in A2. Okay, so meaning we really just attach, okay, every point in A to a projective one line. Okay. And then how do we do this attachment here? We don't look at the whole space. Okay. What instead we look at is we look at the pre-image of some zero set. Okay, let's say pre-image of zero set. We just look at some zero set, okay, inside this A2 cross P1 here. And then what does this zero set do? What's the function? What's the polynomial we are killing? Let's say A2, the coordinate is S1. Okay, and then our P1 is, let's say, T0, T1, right? T0, T1. So what's the polynomial we kill there? How we killing there? What's the polynomial we are killing? Check or not? What's the polynomial we are killing there? Adrian. What's the polynomial we're killing there? What do we mean by kill the polynomial? Okay, so we haven't mentioned about this word quite frequently in this class, is it? So killing the polynomial, just say as setting the polynomial equals 0. We're killing an idea, killing a normal subgroup, we set them to be 0. Yeah, okay, so what's the polynomial, okay, that define the blow up for A2 at a point? Xt0 minus yt1. Is it correct or not? Xt1 minus yt0. You should swap. Okay, because through this swap, right, what are we doing here? Actually, we are asking where this xy point here lives on which line through the origin. Make sense? Make sense or not? Yes? Okay. So let me repeat. So through x t1 minus y t0 equals 0 here, this zero set of this function, actually what it does is it tells you that where the line through the origin that xy live on it. Make sense? Do you remember? Do you remember the picture where we lift up the line through the origin? So the data you keep is I have a point on A2, okay, which line it is, and this gives me a height in the P1 coordinate. Okay, does it make sense? Okay, but inside P1, right, is another line in A2. Okay, although we draw it like R3, like A2 cross P1 is an R3, but really the third coordinate there is a line. I mean bunch of line. Constant line. Okay, so we view it as a point. Okay, so now we want to make it general. Okay, so we want to blow up. Oh, let's blow up affine variety. Okay, let's blow out a general affine variety here. So there are three stages we want to do. We want to blow up affine varieties. We want to blow up projective variety. We want to blow up affine variety at more than one point. Okay, not just one point. Okay, these points we could control by ideal. Okay, so we want to blow along an ideal. Okay. And then in general, we want to blow up a quasi-projective variety. Okay, we blow out an open subset. Okay. So let's see how much we can do here. Okay, so definition. Well, let's see how we put this. So let f0 to xn minus 1. Okay, live in an minus an. Okay, so these are the coordinates in an. And we want some coordinate on Pn as well. Pn minus 1 in particular. Okay. So we want to blow a general an. Okay. Last time we just blow A2, right? So A2 cross P1. Then in an, what are the line through origin? Pn minus 1. Okay. So these are the two things we put together. Then the blow up of an. Okay, we still blow at one point only, at 0. And the 0 point is the closed subset. So let's denote it as an tilde again, which is equals to the 0 set of xi yj minus xj ij going from 0 to, okay. So we take more combination here now, okay, random 2 combination. Okay, so this is the point. Everyone okay with this notation? Huh? It's a bit like mix of set notation and bracket notation. Okay. Okay. So this is just a convenient way to say, like, right now, like let's say y0, y1 minus x1, y0, and then y0, y2, I think, something like that. Right. x2, y, sorry, x, yeah, x2, y0, and then so on. Okay. Okay. All right. So sometimes, right, let's do some notation here. Sometimes we write the whole x to be like this. So we define this point x to be this coordinate, and then the point y as this, as this point here. So we put a bracket for y because we know that Pn minus 1, the elements are equivalent class. Okay, and then what's the exceptional divisor here? So similarly, we have the projection from an tilde to an. Okay. And then we just look at the pre-mesh. Yeah. Okay, thank you. Okay. So we call E, which is E subscript A, E, exception. Everyone okay with this introduction? Okay. Do you buy that this is just a generalization of A2 case? Okay. Yeah. So similar thing we could see here is actually this map here, this projection here is a birational morphism. Okay, birational morphism means what? Its inverse is also rational. Okay, but maybe define not at all the points, right? Okay, not at every point here. So we claim that it is a birational morphism is also defined as isomorphism. Okay, which part is defined isomorphism actually? As long as you look away from the zero. Okay, as long as you look away from zero, it is a isomorphism. Okay, still remember the picture we see in AN A2 case. Okay, at the zero, you got zero across the whole P1. But at the all the other point then is just x with it, x with it. And so away from this zero, right, it should be a isomorphism. Okay? Should be the isomorphism. So I would leave you to verify. Okay, so pi is a projection map, right? Okay, so let's write down this projection map. So you have x with x, right? Okay, then you project to x. Okay, but what's the pre-image here? What's the pre-image here? So really, you could define an back to an star. Okay, so x golf x sending back to x to the line it contains it. Okay, for x not zero. Okay, so this is the birational rhythm. Okay, the y actually is the line that contains x, right? So you could use x to build that line also, because they represent the same equivalent clause. Okay, try and check this is the rational inverse unit. So I put a dot here exactly this zero. We don't know. I mean, we cannot quite do this map for zero, right? We go who contains zero. No one contains zero. Then no one contains zero. So but it's legit. Get to write down the map like this. Although I didn't define for zero, but I put dot here. Okay, so please don't tell this to calculus 1 student. They cannot do this. And by legit in this pattern because this is rational. Sorry， 哪一个是 legit 哈？legit 是合法对，因为年轻人不懂事，他不知道这什么意思。你如果这样写，还有些点define 不到，可以这样写就完蛋了。Yeah, but we know what we should do in this class. Okay, so this one I prove for generalized, so A2 also work as well. And then some property, actually we kind of see from last time already, so we just make it more apparent now. So if you look at this blow up, throw away your exceptional divisor, this is exactly just a graph of the morphism x of an to Pn minus 1. Okay, so basically your s coordinate is this an point here, and then your y coordinate is just the height. Okay, so this is the graph, right? Okay. So yeah, so there's a reason why we write like this. Okay, so we really want to think it like I cannot say R2 but this is a two main part we want to build it. Okay. And then each main part is an n-dimensional thing. Yeah, no? Does that make sense? Okay, this kind of concept is quite important in higher maths here. inside a dimension, you could hide a lot of infinite things inside there. Okay, so this is also a string theory ideas. Okay, what's string theory here? Maybe I give you some idea here. So let's say what is 3 dimensional? What is 2 dimensional? What is that 1 dimensional? Okay. Maybe you might think that going down, right? But if you look at this 1 dimensional, right? Maybe if you look far from when Trump place, right, it's just a line. But if you look from my place, it's a cylinder. Something break in this world. You look from far, it's just a line, right? But if I look from here, it's a cylinder. Huh. So inside a world. 就他在讲佛经啊，佛经不是讲里面有3000世界吗？Okay, but I mean like, so string theory also like that. So when people try to figure out how many dimensions I can control this world, 26. 26 is enough. No, we don't say we must reduce to 10. Supersymmetry, we can reduce to 10. 10. How come got 10? I thought our world is 3-dimensional. Okay lah, at most lah, I plus a time into it, 4-dimensional. Where's the other 6-dimensional? So if you look at every point in the world here, there's a 6-dimensional thing here, which we call the Calabi-Yau manifold. Okay. So there's a promotion here. This afternoon, there's a knot theory class relating to Witten physics. Maybe you can come. Yeah. Maybe you can come. Okay. Actually, because my work related to this knot theory stuff. Okay. Right. So this is a graph. Okay. Graph of this. Okay. I don't need to explain too much, right? This is okay. You buy this sentence. Buy or not? Buy what? Huh? You buy this sentence? Where's the notation? Proper. Where the notation? Oh, the dot.啊？哇，号是什么？bracket bracket 等下。Square is for what did we decide? I forgot already. Did we use the round or square last time? Huh? Round. Round. Yeah, how about this? If I put this, then this is dot. If I put square, then this is a comma. Make sense or not? Like this? I think this one makes sense, right? Because this is equivalent class, so it's the equivalent class of a point. But the above one is the how the class looks like. Okay lah. But if I really confused, there's a permutation between these two. I think you should know. But just that maybe it's my typo. But we shouldn't have it, but sometimes life got some problem, right? Life always go wrong, right? What? You cannot run me away from the philosophy. Okay. Another thing is this blow up, right? Also has an open cover. And this open cover is not hard to describe. So what's this open cover here? Basically, it's just Vj. Okay, Vj is defined to be over the x and then the point y such that the yj component is not 0. Well, basically, it's just use the pi cover to cover this thing. Okay, use the pi cover pi. And then this is the affine cover, right? Last time we showed that it's isomorphic. Okay, so what's the isomorphism here? let's remind you what's the isomorphism here, but now we got the extra stuff. Okay, so here there's a isomorphism. So from phi j, from Vj to A n or n a minus 1? an or an minus 1 here? Which n? Which n? What do you think? Last time our Pn affine cover, right? Go to which n? Just an. Okay. So you should think of the Pn, right? You can cover with a lot of an. Pieces of an. Okay, so what's the map here? I should tell you this map here. So you have a point called x and bracket y, right? Where you should send it to? You should send it to this point here. Sj, I pick up one xj, and then how do we deal with the yi here? So we divide it by ij, and then I exclude yj over yj. Okay, so to mention it get excluded, I put a hat of it. Okay, so how many variable here? Here got n, right? I throw away one, n minus 1, but plus 1 coordinate back, so got a. Okay, enough. Obviously, we need to prove this is an isomorphism, but okay, right? And so in this case here, what can you see here is an cross pn minus 1, right? Is covered by a bunch of an. Okay, covered by a bunch of an. Okay. Okay. Next. So this blow up here is irreducible. Okay, it's irreducible and smooth. Okay, it's a smooth. Moreover, it is the closure of the graph that we mentioned just now. Okay, it's the closure of the graph just now. And then third, if we look at the isomorphism on exceptional divisor here. Okay, so if we look at the isomorphism on this divisor here, so what exactly is this? Okay, so actually this is a zero set of the Sj component. Okay, so meaning if you look at E at this Vi here intersect with Vi here, okay, actually it's just a zero set of the J coordinate function. Okay, we will prove this. And then lastly, E is what? E is just 0 cross a n minus 1 projective space. And previously also like that. It's just a point cross the P1 line. Okay, let's spend some time proving this, and then we will take a break from here. Okay. Wow. Well. So let's do this first. Okay, so let's get some point in this pre-mesh of an cross 0. Okay, so this is the point inside a tilde here. In particular, a tilde / e, because we are not looking at the pre-mesh of 0. And then we want to demonstrate that this is a graph, okay, of S. So meaning it's a The y coordinate, in particular, the y coordinate here can be expressed as x of something. X of what thing? If this is a graph. Graph means what? X, fx. Okay, so meaning this point of y here should coming from applying this s here on x. Okay. So how do we prove that? What's this s here? This s here already do most of the job for you already. This s here says what? Get a point sent to the line contained it. So the thing you need to understand here is why this y is the line that contains x. Why this y is a line containing x. Okay, but how do we get this y? I still remember not. How do we get this y actually? It's a zero set of the xi, yj minus yj xi. But that zero set is actually helping you to picking out the line. Okay, so if we assume x0 is 0, okay, if x0 is non-zero, then if x0 is 0, then you can look for other xi, is the same thing. Okay, then what can you see here? Now I'm demonstrating to you why it makes sense to make our blow up using the zero set, using the function look like that. So let's say your x0 is non-zero. What you can get is a bunch of x0 yi minus xi, y not. But this will turn into what? This will turn into yi equals to yi over xi equals to y naught over x naught. Okay, but what does this mean here? The ratio is the same. What does this mean here? The ratio is the same. Ratio between yi and x0, xi is the same. Meaning what? Their ratio. Their ratio is the same. Means what? They are on the same line. Their ratio is the same. So one is a multiple of the other. Okay. So indeed, our point can write as x as x. Okay. So that's why we make that zero set condition there. Why got I and j different? Because maybe you have x0 to be 0 and then xi to be non-zero, something like that. But you cannot have all the coordinates to be 0, right? Because we are not looking at the 0 point. Okay, so this is good. How about the second one? So you have that give the map already. Okay, this question is much easier, you know. You should imagine that at first sight, how people think about this. Okay, if people already tell you this map, right, they already do the hard job for you. What you need to do is you find the inverse. Okay, what could it be? The inverse here. So I give you a point in AN. You need to cook out a point in VJ. VJ got how many things? VJ got two parts, right? One part is AN, one part is PN minus 1. Okay, so how to cook the two things out? Okay, well, so that's a very clever thing to do here. So similarly, let's just do for one of the j. So let's start with j equals 0. And then we will write this z here as z1 up to zn. So, okay. So for let's set, okay. Let's consider this map here, V0. Okay, V0 is from AN to V0. Okay, so how do we do this inverse map here? So we have, let's start with T and Z. Okay, first coordinate here is a bit special. Just as how special SI is to phi I here. So what we're gonna do is we will create the x point and y point here. So how do we create x point and y point here? Well, we'll put the x point as t and tz. Is this the right dimension? So z have n-1, and then you add a t is a n-dimensional. Okay, it's in an. How about pn-1 here? So what we're gonna do is we add in this point. In bracket 1z. Is this the right dimension? 1z, how many coordinate here? N coordinate. Okay, so it's an. So you projectivize an, you get pn-1. Okay, right space. Okay, so once we got these two functions, right? So let's try and compose them. I let you try. You try and compose them. Try and compose them. See what you get. Try and write down your notes or anywhere. Try and compose them. See what you get. Try and write down. Okay, one thing you should know how to verify is you should know how to compose these two things. Okay, after composing, is it an identity or not? Yeah, try and compose them. Try and compose them. I think one direction is kind of obvious. The other direction, you really need property of blow up, a defining property. Okay, so let's do the first one. After you do V0 at this point, okay, this is what we have just defined, is just ETZ and 1Z here. But what does phi 0 does to this point here? You just pick up the S0 point. Okay, in this case here is T. And then what do you do next? You look at your Y, okay, and then you throw away Y0 over Y0. But Y0 over Y0 here is 1 over 1. And then Z over 1 is still Z. Okay, so you get Z here. How about the other direction? So we get x0 and then y1 over y0, comma, blah, 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 blah. So you note that there's already one term I throw away, right? Is the y0 over y0 here. Already get thrown away already. But what is v on this thing? What's v on this thing? Like Lydia, must know how to compute this. Only then you know why we define blowout like this. So how to compute this v0 on this thing? So v0 on that thing. So you view x0 as t, z as the rest here. Okay. And then the top, what do you do? What do? You do substitution. Okay, let's do substitution here. Okay, substitution. What do you get for substitution? S0 and then S0 on every other thing. Right? Or not? And then comma 1 of all the other thing. Does this look familiar or not? Does this look familiar? Familiar or not? These are the points on the zero set of blow up. What they satisfy? Huh? What do they satisfy? X0, Y1 equals to Y0, X1. So you pull your X0 here, what do you left? Xi. So what do you get? X0, X1, blah, 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 blah. And then up to X n minus 1. And then comma. How about this point here? How about this point? How about this line here? This is just a representative, right? We can multiply Y0, of course. Okay, so you see why it makes sense we define the zero set like using this function because we can retrieve them. Okay, I just use a single y0, single x0 and a single point in y here as a y here. I can retrieve the whole thing already. Because I know there's a polynomial equation there to, a set of polynomial equation there to satisfy. This set of polynomial equation, I just need these two pieces only. Okay, I just need these two pieces. What's this two piece here? This piece here. Yeah, I just need this number. I can retrieve the point in my blow up already. Not every point, because this is just affine, like just covering, right? Part of them I can recover. How to recover the other part? Use a different covering. Okay, use a different covering here. And use a different covering. Then you can retrieve all blow up. Make sense? Does it make sense? Okay, you see where you use the zero set here. These are the point that can be retrieved from your zero set. Make sense? Okay. So can you believe this isomorphism here? Can believe? Yeah. Yeah. Because this isomorphism is quite significant, because in the VJ, right, the space is like AN cross PN minus 1. It's like AN cross AN somehow, right? AN cross AN. So it's A2N. You just use AN to pick it up. Half of the dimension already can pick up everything. Not everything, but one part of it. Then half dimension, or you can pick up part of it already. So actually, this A2N is not very big, actually. It's not really big. If you see from this viewpoint, every part is just AN only. Although the whole space is it's like two times larger, but the real blow up is just the blow up of the surface is just OAN. Okay, makes sense? Okay. Okay. How to prove irreducibility? Okay, how to prove irreducibility? You need to show that every open set have a non-empty intersection. Okay, but in this case here, you can reduce the statement to every open basis element. Okay, you can reduce to basis element. And then last time we proved that these VI, right? Distinguished open set. We didn't use this word, but I write out in the note. Distinguished open set means what? For those points that the J coordinate is non-zero. Why are they distinguished? Because they are the complement of a Sj equals to 0 set. Okay. So these are the basis element last time we mentioned. So you just check that this basis element has non-trivial intersection is enough. Okay, but I think it's easy to see that this Vj has no empty intersection. Actually, Vj quite big. Yeah, Vj is actually quite big. Makes sense? Does it make sense? What's the picture you have to have in your mind? Let's say P1. What are the V1 and V2? So V1 is like this. Correct? V2 is, yeah. So these are the open bases. So they have a lot of intersection one actually. You can check by set theory also. Okay, check set. And it's not empty. Okay, so let me write here. So check on basis element. We call it what? So dxi, okay, which is equals to a is it? Let me think. Yeah. So throw away bi. Okay. Sometimes people call this vi as a hyperplane also. Yeah, somebody call it hyperplane also. Complement of a hyperplane. Okay. So if you remember, my friend come talk about hyperplane, right? So these are just object. Okay? Object by itself is interesting, right? For sure. But we are algebraic, right? Algebraic person. We study about group action. Okay, we want to see how group act on this surface, how these hypersurface change. Okay, so there's a group action. And it turns out that group action is another manifold. Group action is another manifold. Okay, then so there's a correspondence between a function and space itself. Okay, they are correspondent. Okay. How about smooth? How to show smooth? How to show smooth? How to show smooth? Well, to show smooth, you just need to count your dimension of TPB, right? And then you show that what do you need to show? A point is smooth if and only if. What's the definition? Dimension of tangent space at that point equals to the dimension of V. But how to define dimension of V? Is the minimum of all the dimension of tangent space at all the points. Okay, but our space is covered by these affine spaces. So at all these points, right, they are just an. They are smooth. Okay. So all of them are smooth. All these points are smooth. Okay, because the point in AN is smooth. Okay, because I have this isomorphism, right? This birational, right? Birational equivalents will preserve dimension. Correct. Two variety are birational, then their dimension is the same. And this is what we have shown last time. Yeah, smooth here because it has open cover by affine spaces. Okay, just now we showed it, right? All these VJ are affine. I think there's one gap we need to show here. Dimension of an open set equals to a dimension of a variety. Yeah, for irreducible part. I think I'll add it into the tutorial. Okay, how to link about opens, how to think about open dimension of an open set inside V. Yeah, I should add it in think to make this complete. And then it's a closure of a graph of X, I think. Is it obvious? So this is closed, and then that graph is an open subset inside there. The open subset. Yeah. Okay. And then yeah. So that graph, why is it a closure of that graph? That graph, there's only one thing it misses. It is the pre-image of 0. Yeah. And then your 0 set of that. Okay. Okay. Two more. Okay, two more very quick. Yes. Yes. Sine. Yeah, sine. Sorry, 我自己在签咩？有在签咩？Okay. Let's change this to 5 then. 我那里解 sine 再看下。哦，OK，我看看哪里有这个位置哦，来让它连在一起。Peanut。Okay. Thank you. Yeah. How about this? How about this point here? Okay. So again, let's show for one of them first. Y equals 0. Okay. So by definition, if I apply y0 on x, y here, what's the point I get? So let's recall again. I just pick out the s0 term, and then I throw away y0 over y0, and then I divide every yi by y0. Okay. Okay, so this is what we do here. But if we use the isomorphism, right? Okay. If I use the isomorphism, V0 on this point here, what do I get? Okay, so what do I get here? So I multiply Y0 on all these fraction, right? Blah, blah, blah. Okay, and then I put back my Y point here by introducing 1 at the spot that I throw away the coordinate. So what does this mean? So these two things should coincide, right? Okay, because they are identity. These two things should coincide. Okay, these two things should coincide here. So we see that if xy is in E, then what should happen here? What should happen here? So if you look at pi of pi of V0, okay, what should I get? I should get 0 because I'm just projecting to the AN part. So E is 0 cross something, some point. But if I project it down, I should get 0 here. But what does this mean? Look at this projection here. Okay, this means that this coordinate here should be all 0. Okay, but how to make sure this coordinate is 0? How to make sure this coordinate is 0? Even if you can make all these yi to be 0, it's not enough. You'll need to at least make your s0 to be 0. And that's the only way. Okay. So s0 must be 0. Okay, so meaning in this point here, look at this point here, is actually the 0 set of y is x s0 equals 0. Okay, or the 0 set of x0. Make sense? Okay, so if you want to plug this point into it, and then you get out some point here, okay, this point actually have to be the 0 set of x0. Okay. Or let me write down here. Let me write down the full thing here. Hence, okay, y0e here is just a bunch of 0 or y1, y0, y2, y0, blah, 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 up to yn 1 over y0. But what's this? This is just a 0 set of x. Okay, you just kill the coordinate. Okay, yi doesn't matter. Make sense? Okay. And lastly, very last, okay, then we will go for a break. So very last here, so what do we have? Here is how do we show this? By definition, show by definition. E is a pre-image of 0. But what's the pre-image of 0 here? This is just 0 across all the projective point. Okay. Such that what? Y0 or y0 times y1 equals to 0 times yj. Sorry, yi and yj or oj. But what is this? Actually, you put this relation like you never put it, right? You put the relation like you never put it before. Okay, so what do you get here? Basically, you include everything. Okay. Yesterday, Trump saying one phrase I like it a lot. Hey, Pfizer, which side do you take? US bomb Iran. Did you take any side? You are neutral. Okay, neutral, then I can talk about it. I mean, like, Trump after Trump bombed Iran, right? Trump said we have a very good comrade, okay, Netanyahu. Are you sensitive with Netanyahu or not? You yes, okay, okay. I speak less name about it. Let's call it a Netanyahu. Okay. So he said I work with Netanyahu as a team, like no team in the world did it before. Very funny. Do you think it's funny or not? I mean, like, very interesting adjective here. Do you understand what he said or not? Like, you work very closely with him, and then like no one worked that closely before. 就很有趣，没有趣。
就没有
I mean, like, did anyone can speak like that? Did anyone speak like that before? Did anyone speak like that before? Confident, huh? Yeah. No one as confident as Trump. But anyway, we'll see how it goes. Okay. Any question so far? Any questions so far? Okay, no. Let's take a break. Let's break until 118.
Yeah, that's right.
写上死我不是，我才吃了肚子又痛，好脏哎，很久没有吃了，吃下去我肚子疼。Okay, we'll continue. We'll use a slide to go because the idea is the similar already for now. So just now we blow out AN, right? Now we want to blow out a subset of AN, okay, which is the algebraic affine variety here, irreducible algebraic set. So how do you blow it up? Well, you just look at the pre-mesh of that set. Okay? It's the blow up of S tilde. And then you will define exceptional divisor for X tilde as well. What do? You restrict first. Okay, you restrict your pi to just S tilde. Okay, and then you look at the pre-image of 0. Okay, using that restriction. Okay. Does it make sense? Does it make sense? Right, because when you take closure, right, you will somehow fill it in on your previous project, except the point in the exceptional divisor, and then when you map it down, those points will go to 0. And then now you look at the pre-mesh. Basically, is the limit point of this pi inverse of x cross 0. Basically, is the limit point is this closure. Okay. And then one thing you can prove is S tilde is again irreducible, and then you have isomorphism using the projection map. Okay, and then this is what we call a strict transform. Okay, and then there's another thing called total transform. Right, last time strict transform is just filling out the pre-image, but total transform, you take these pre-image plus the exceptional divisor you get from your AN. Does that make sense? Okay. So from the picture we had last time, right? What could you imagine? Let's say your curve is like this, right? Okay. And then you fill it in, you fill it in. Okay. But what's the total transform? You need to include the exceptional divisor you get from your surface. And that's a total transform. And differentiate total transform and strict transform. Okay. So strict transform is perhaps just this green line here, but total transform you need to include the whole group. Okay, and then if you want to blow up at the other point, you just shift your x to that point first, and then make your point 0, and then you can apply the 0, blow up, the blow up at the origin. Okay. So you can see a lot of construction here about at different point. You just shift it. Okay, so that's why we are interested in affine space only, because we can always shift the origin. Okay, just translate it. Okay, this one I think you can appreciate later. Okay, for blow up for x, right, we have another construction for polynomial, which we call the initial degree. Okay, so what's the initial degree here? So this is the minimum I with fi is non-zero. It's this I. Okay, this fi here is the ith homogeneous part. Yeah, ith homogeneous part. Correct. Yeah, it's the ith homogeneous part. Okay, so this one be this notation here. I need to specify a bit. Ith homogeneous part. Okay, so in particular, if you look at this kind of polynomial here, can you recognize what this polynomial trying to do? On all your coordinate, right, you must have a single factor S naught. Okay? So you imagine, okay, you have a polynomial and then every variable you have an S naught factor here. Then you should be able to pull out X naught from every term, right? But how many of them you can pull it out? Factorize it. How many of them you can factorize it? So we try to use this IF to factorize this S naught part. Okay. So what we do is, let's say the minimal term is Fi, right? Okay, so we call it FIF there. It's the minimal one. So for the minimal one, I can definitely pull out X naught of IF. Why can I pull it out? Because every factor here must contain at least one S naught. So it must contain IF of many S naught there. Okay, and then the rest what I do here, the rest is more than IF, right? So IF plus some J, okay? And then inside here, I only can pull J of them out. Why? Because IF already pulled to the utmost already. So this bracket is look like this, huh? This bracket is like this. The bracket is like this. This is the bracket. Okay, don't see wrongly, not this one. Okay. Make sense? Okay. 哇，越来越想去厕所了。阿切，有没有人可以帮我们代课一下？我现在准备好。我真的要去厕所。大家一起研究一下这个slide，我聊回聊天。谁帮忙代研究一下？七位还是温川来代课？我要上厕所。You can wait and then slide through the slide， 讨论一下。文川来了，文川来，他们带一下 discussion。等下我回来。 So you have that. Right. Yeah, they're already. Yeah. So you're fair. That's not. I thought. So, that you are.没有，这个没有成本。
我是 recall 一下前面讲的东西。我说我只在 recall 一下。
Oh. Okay. So how's your discussion? Huh? Got discuss or not? Okay. So we talk about this initial degree here. Okay. Okay. And then we will make some similar statement on blow up here. So first proposition you will see is every irreducible component of E has dimension lim x minus 1. Okay, in x tilde here. So in where is it? In A tilde is also the same, right? Wait, let me see. Every irreducible component of E. What's E? So E is the exceptional divisor here. If we call it E. Yeah, okay, so we call it as a exceptional divisor of E here. So it has dimension x minus 1. Okay, do we have it just now? irreducible. Okay, I think we don't quite have that. We didn't show that. And then I of 50 of x tilde here is this polynomial. This set of polynomials. So what's this set of polynomial? This is fraction of f by divided by x to the j of the x naught coordinate. So what's this j here? This j here is controlled by if. So just now we introduced what is if, right? So if is the maximal. Let me see. Is the minimal. Sorry, is the minimal with f the I homogeneous part to be non-zero, but it is a maximal such that it is divisible by s naught, the whole polynomial. Does it make sense? Okay. This is not true in general. This is only true for this kind of polynomial. Because all your coordinate, you must replace it by at least one factor of x naught. Okay, so that you can pull all the correct number of x naught out. Okay, and then E. Okay, what's E here? So this is correspond to what we did last time. Remember that last time when we pull out the curve, I told you that in the intersection with of the blow up with the exceptional divisor of surface is the tangent line, right? Okay, so this is correspond to what we have done last time. Actually, your E, okay, this E is correspond to the exceptional divisor for your x. So which is E, the E of AN intersect with x tilde. Okay, it's actually the projective tangent point. Okay. So this proves that actually the intersection there actually is the tangent line. Okay, it's the tangent line. Okay. So this proof here go through this technical definition here. Okay, maybe we don't discuss this proof. I write it for you. You can read it. Okay, and then actually when we go through this proof, there's a little bit of commutative algebra you need to know. So I also add the commutative algebra part in for you to check. But I think for this purpose, you don't need to quite understand this commutative part. Just that I want to keep my logic complete. Okay, you don't need to like learn how to prove this thing, although it's not too hard. But oh no, it's hard actually. This one is hard. But I will give you another way to prove why if you have a dimension of x, okay, you intercept, if you take your alpha variety, intercept with a hypersurface, why the dimension decrease by 1? Okay, actually follow from some commutative algebra. I will provide you another proof in the tutorial, but this is one way done by Ernest Kunz. Okay, Ernest Kunz. Okay, I will show you another way to see why if you have a affine similarity, you slash out by a hypersurface, why the dimension decrease by 1? I mean, intuitively, you would think that it's decreased by 1, right? Cut by 1 dimension thing. But why is it true in general? It's a bit technical. Okay, so the presentation of around this lecture, you will find a bit confusing because some of the statement is I introduced afterward. Yeah, it's not like, oh, I do this, then this happened. It's like, this happened, why this happened? Only then I write down why this happened. Okay, so I think it's not too hard to follow if you really go follow my pace here. Yeah. Right. Okay. Okay. So the examples here is we can use the definition above to do blow up. Okay. Last time we do blow up by some change of coordinate isomorphism, right? But this this proposition here really tells you what you have to do with your blow up. Okay, this proposition here tells you what you need to do with your blow up. Okay, what's this largest maximum S0 that you can pull up here? Okay. I don't want to teach you mechanically, can I? 可以吗？懂什么意思啊？我不想一步一步教你们，但是我想跟你们讲做，你们自己去想一下，讲一步一步把它写成，可以这样子做，可以啊。我觉得你们要长大一点，就这样，我只能够讲，不要长大是你的事。OK，就这样。So what we do here is like what you see just now. We replace if we look at any chart. So what? Okay, let me tell you what is happening now. Yeah. So you see, to figure out the blow up, right? You see this what is this doing here is I look at this blow up at some chart, 50, right? I look at some chart here. Okay, but it is still a point on S tilde. I just look at different chart. So at different chart, in particular, this is a 0 chart, right? Then you need to do this thing. Okay, what's this thing here? So you take your defining function, go and substitute this bunch of thing into it. Okay, then now you can ask yourself, what is the minimum, okay, or maximum? What's the maximum xi I can pull it out? Makes sense or not? Because every term already got s naught, right? So you can ask yourself, what's the maximum x naught I can pull out? Okay, then you divide this function by the maximum x naught you can pull out. For example, okay, give me an example. This case here, okay, this example, this is the sorry. So look at this example here. This is the x I want to blow up. Okay, and then I want to blow up at some chart v0, t0 not 0 0. So what do I do here? I substitute s naught as x as s naught, and then y as t s naught here. Okay, what's the maximum x naught I can pull up? 1 x naught. Okay, so after I do the substitution, I divide by s. Okay, here the x naught here I call it x naught. Okay, so you can see that actually these are just parallel lines. Okay, after blowing up. So this corresponds to this corresponds to what? This corresponds to, so imagine the picture in A2. This is just the A2 picture, is the same picture we see last time. A2. And then if you fix an A, right, it's just y equals to ax. Okay. And then after you blow up, what happens? So this is these points get moved to different height, right? Inside the blow up. Okay. And then the point here is if you disregard the s coordinate, in the pi coordinate, these are just different line there, parallel line in P. You can squish the x coordinate. If you just remember the pi coordinate, the y coordinate. If you just look at the y coordinate, it's just parallel line. Can make sense or not? Let me draw this picture. I hope I'm drawing it correctly. So this is your A2, right? Then let's say we take this. This is your 0, 0 point, and it is y equal x, say. Okay, you blow it up. Okay, after you blow up, maybe you get something like this is what is these point? These let me think. How to draw this blow up? This is just different point at the same height. Different point at the same height, right? So let's say this is 1, right? I think your line is something here, right? Okay. Okay. But the u minus a, where's the u minus a here? There's a u minus a here. Now u m minus a is this line. Not quite this line, right? It's the this height here. Okay, u minus a. So why we say parallel line here is because if you look at all these different lines here, okay, they are all parallel line. Okay or not? Makes sense. If you look at all a family of line, this is what I meant. Or if I fancy a bit, this is the moduli space. Okay, family of line. Okay, then these are parallel line. Okay, because they are at different height. This U here control the projective coordinate. Makes sense? Does it make sense? Okay. If you compare to what we compute last time, you can compare one. Okay. I don't force you to not compare. You should compare. So if you compare from what we have computed last time, so where is it? Like this lecture here. Okay, if you compare here, you have extra coordinate bringing up here actually. Okay, this is something that we throw away just now. Okay. Okay. If you notice that the picture we draw for this graph is really just this bit here. Okay, if you notice this picture here, okay, it is the split that we hold up. Because s squared times this equals 0, s squared equals 0, s is just 0. Okay. Yeah. So this is the bit that we draw out actually. Okay, so that's why in the simplified version of that we compute this now, what computed by that formula is actually this bit here. This is the bit. Then this is the IF that you can pull out. Okay. Make sense or not? Okay. Okay. Okay, and then similarly you can do for different things, okay, different kind of line. And then I also attach a bunch of example for you to appreciate. Yeah. Sorry that I cannot make it a recipe for you to follow, but at least I want you to follow the idea. Okay, I want you to follow the idea. Okay. I still want to emphasize that idea first and then method second, because we are trying to do research. Although I cannot deny that method is very important, but idea is come before method. I want to say this. You might think that, oh, 哎呀，老师，我都动不了手，我怎样做？ Yeah, true, very true. I'm also the same. But slowly you will realize that why you have this kind of idea was actually you are not quite sensitive with concept. There's a deeper reason why you keep asking about method is you are not quite sensitive about concept. I don't deny that you can go and find method, but I want you to go a bit further. Okay, ask yourself, what does this method can do for me? Because from our viewpoint, from bird view, we don't really care about method actually. And moreover, maybe method could update along the time. Concept won't update one. You understand what I said? Method can change, but concept won't change. Over time, method will increase one, will be better one. The time when I learned product rules, UV prime, is it product rule? Chain rule or product rule? Chain rule or product rule? Last time we learned. Let me think. No, integration by part. Integration by part. When I learned it, we just do like UV minus VU prime. UV prime minus V prime. But now they got something like these, and then like these, got something like this. What is this? I never learned about that, man. But I saw someone already using it. Doesn't matter. All of these just serve a purpose only. Just serve the purpose of integration. Okay. Yeah. But now I think, yeah. Oh, hopefully you understand that. But I know that it's very hard to change this mindset. But yeah. But let's work together. Okay, I will help you. Okay, please come to my office. If you want to pay me, also can. I don't mind. Okay. Yeah, I put a bunch of examples for you to see, and then you could see that these examples are there are slightly different argument here, but doesn't matter as long as they answer everything. That's good. So okay, there's a D6 here. I mean E6 here. There's an example of E6 here. I think someone you're doing these examples, right? Drawing up these exceptional devices here. Okay, I'll put a bunch of example here so that you have an enormous example to see. Make sure you know how to do blow up. Okay. Then if X is in the dimension D variety here, what you can see is actually its actual divisor is 0 cross the projective space of T0x. But here the 0 point is a smooth point for X. Okay. Just now you see tangent, right? Sorry. Just now you see tangent con. Just now you see tangent con. But now you see projectivized tangent space because this point is already smooth. And once it is smooth, just last week we showed that tangent con equals to the tangent space. Okay, so just now, if you blow it out, it's just a CP0, projective tangent con. But now if it's a smooth point, then this projectivized tangent con is just a projectivized tangent space. So the point here is why I cannot projectivize, why we call the tangent con projective tangent con. Tangent con might not be vector space, you know. What's the difference between con and vector space? What's the similarity? What's the difference? Tangent space close, vector space close under addition and scalar multiplication. But con only close under scalar multiplication. But this is the thing that I can do projective. Why projective? Because projective make a line into a point. So scalar multiplication is more important here. Addition not really. So the point that we can projectivize this tangent space here is not because not all the vector space property we need it here. How we projectify the space as long as that space has this close under scalar multiple property. Okay, so meaning if a point in there, the whole line must be there. Then when I projectivize, meaning I regard the line as a point. Okay. So projectivize always just means that, oh, I regard a point as a point as and regard a line as a point. Okay, and then all points in E are smooth point of X tilde. Okay, so meaning this just says that if you look at the pre-image of smooth point, they are smooth also in S tilde. This is what this proposition was. Okay. If you blow the smooth point up, it will still be smooth. Okay. Yes. Sorry. Why? Why? Yeah, sure. I mean, like, no, we did define that this E is whether what kind of E is it. So maybe this E should be X E of X tilde like that. When we don't specify E of what thing, it should be appearance of what kind of E we are talking about. Okay, I mean like yeah. So whenever we talk about exception divisor, we should talk about whose exception divisor. So you need to think about whose one. Okay, to discuss here. I guess for in this case here should be a blowout of S tilde. Okay, then we can blow up projective varieties here. So how to bridge these two? So we fill the 0 point at so we use open cover to identify affine space with projective space here. Okay, so if we want to blow up Tn, right? So this point here must live in some affine space. Okay, when I say affine space here, we are already apply the isomorphism. Okay, using the open covering. Okay, so you can see that the 0 point here could be 0, 0, 0 something. Okay, 0, 0 something 1 here. You could not have all 0, right? Because 0 is not in projective space here. And then you do the similar construction. Okay, you do a similar construction here. So Pn will cross with Pn minus 1 here. Okay, does it make sense? Pn cross with Pn minus 1. Make sense? Let me think. So you have a Pn, right? So Pn, you have An. Oh, makes sense. Okay, makes sense. How to make sense of this? So Pn is a line in An plus 1, right? Okay, I cannot think like that. So Pn has an open cover. But this open cover is isomorphic to An. And then you can look at the line in An. And then this line in An is Pn minus 1. Okay, so that's why Pn cross Pn minus 1. Does it make sense? You know how to make a bridge. So you have Pn, right? And then you use affine standard cover to cover your Pn. And then this standard cover is just An. And then go from below it there. Okay, so line in An is just Pn minus 1. So that's why cross with Pn minus 1. Make sense? We go back to the affine case. How to go from projective to affine? You cover your projective space using affine space. Okay, and then you blow, same theory come out. Okay. Let me see. Okay, just blow it. Okay, blow. Okay, there's one lemma that I don't think I want to discuss here, but you can look it up. I pause it here also. So if you blow up P1 cross P1 at a point, actually it's isomorphic to P2 blowing up in 2 points. Okay. Actually, this thing might not be intuitive, right? So you might think that, hey, P1 cross P1, why not just P2? So you blow out at 1 point, also blow out at 1 point there, right? But it turns out that actually you are blowing out 2 points in P2. Okay, to get this P1 cross P1 here, blowing out at 1. Okay, what time is it? Let me go a bit further. So next, we can blow up along an ideal. Okay, so how to blow along an ideal? So what do you do when you blow out at a point here? So you view it as blowing out at a maximal ideal. Okay, but if you blow out at an ideal, you take an ideal there. After you do the blow up, you take a point in X. How do you blow up? So you have maximal ideal corresponding to this P here. And then xi here will become your coordinates. Okay, actually these si are the generator of MP also. Okay, makes sense. The projection you looked at all is a generator of your MP. Let's say my P is 0. So this coordinate function is actually the generator of this ideal, this MP ideal. Okay, and then what do you do? And then you look at this graph here. Okay, literally sending this x to the equivalent class of this x here. Okay, and then you look at the projection from this graph. So in general ideal, what do? You have an ideal. You also have generators. Okay, and then you look at this rational map here. Send x to fix. Previously, your fi is what? Previously, your fi is just xi. Now you send it to fix. Okay, and then your blow up is this graph here. Make sense? Does it make sense? So you replace the projection map you had just now. Those are the generator for your maximum ideal. But now you take a new generator, maybe fi. Okay? You apply on x, and then you look at the line that contains this point. Okay, this is called a blow up along an ideal. Makes sense? And then you need to prove a similar statement. But one thing you need to show that is this graph here doesn't depend on the generator of y. Okay, this is something non-trivial here. Okay, and then you can do a similar stuff here. Okay, do a similar stuff, and then you go and blow up quasi-projective variety. Okay, why we can blow quasi-projective variety now? Because we are blowing out a homogeneous ideal. Okay, we can blow along the homogeneous ideal here, and then after blowing up, there's a very important singularity theorem here is if you do this kind of blow up, okay, you blow up as a singular point, the thing that you blow might be smooth, might be not smooth, but there's exists a finite step such that the blowout will be smooth. Okay. Makes sense. Okay. Hey, just now, by the way, we didn't prove that S tilde is smooth. I just proved that A tilde is smooth. Okay. I didn't prove any S tilde is smooth. I just proved AN tilde is smooth because AN is smooth. Okay, but if X is not smooth, then S tilde might not be smooth. But the point here is after a finite step of blowing up, it will become smooth. Okay, so this is a Hironaka desingularization theorem. So this statement is a statement on quasi-projective variety. Okay, I put a bunch of reference for you on the Moodle if you are interested. Yeah, so you can see that how it advanced across years. Okay, they first prove it for characteristic 0, and then characteristic 0 proof also become easier, and then you can see that Kutkowski proved it for positive characteristic. Okay, right. We'll continue tomorrow. See you tomorrow. Cool.